In this video, we're going to discuss the characteristics of polynomial functions. You have seen a lot of these characteristics of polynomial functions. You've just seen them with the lesser degree polynomial functions, such as quadratics, right, degree 2, and linear functions, degree 1. And today we're going to take those to any polynomial function of any degree. And it's really important that you be able to apply what you've learned in the past and build upon it as we move into higher degree polynomial functions. Let's start with zeros. You already know what zeros are. What are some other words that also mean zeros? Roots would be one. X-intercepts would be another. Solutions would be another. So hopefully you're looking at this graph of a polynomial and you're like, yep, I can locate all the zeros. So one of your zeros is that x-intercept. Here's another zero. Here's another zero. And here's another zero. So there are 4 zeros, which will become pretty important as we start to identify polynomial functions and their graphs. Another thing that you should be able to identify is the y-intercept. So this here is not a zero. It is the y-intercept. And one thing that you've learned, especially in dealing with quadratics and linear, is that the y-intercept is always the constant. So that's any time that x is equal to 0, and then you have some constant. We'll call that constant c. Now, I created this polynomial function in Desmos Graphing Calculator, and I just created like a random polynomial just to give you an example of a higher degree polynomial graph. We'll call this one f of x, and here's the function that I have for it. Notice all the terms. But also notice that our y-intercept looks like it could be around 1, and that just happens to be our constant here. So that is the same as our y-intercept, which truly is 0, 1. Hopefully that's really familiar for you. Now I just gave it away the degree of this polynomial function. If you look at the function itself, the leading term has a degree of the 4th power. So the degree of this polynomial function is in fact a 4th degree. Now moving forward, I'm not going to identify the degrees of the rest of the polynomial functions in these notes. So you'll see I have a whole bunch of different polynomials that I've created through your exploration in class, where we are on Desmos doing kind of an exploration of all of these polynomial functions. You should then be able to come back and fill in the degree of every single one of these polynomials. Okay, the next characteristic is end behavior. Now, there are different types of end behavior. The first type of end behavior is when the end behavior is going in the same direction. So notice the polynomial function that we just talked about, the x to the 4th power, f of x up here. Notice that both the left side and the right side are both facing up. That means that they have the same direction end behavior. And notice this polynomial function that I gave you down here to the right, also both going down, but they have the same end behavior on both sides. Now, there is a way that we write about end behavior, and I'm going to show you. So, when we have end behavior that's going the same direction on both left and right, we can talk about the outputs going the same direction. So, for both of these, well, let's start with this one to the right here. You can see that our outputs are both heading down. They are getting more and more negative as this graph. If I went as far to the right as I possibly could, right, it would just keep getting more and more negative. And if I went as far to the left as I possibly could, it would just keep getting more and more negative. So what I can say about this polynomial function is that as x gets large, or as x goes to infinity, so what I'm talking about is as we go to the right on the x-axis, what's happening to the y values, or what's happening to our outputs? Well, they are getting smaller and smaller and smaller. So we'll say f of x, we'll call this function f of x, is going to negative infinity, which is just an expression for saying it's getting smaller and smaller and smaller. And as x, now as we move to the left and x gets smaller and smaller and smaller, we can say as x goes to negative infinity, what's happening to our y values? Well, as our x gets more and more negative, it looks like our y values are getting more and more negative. So you see how our y values take on the same exact behavior no matter which direction we're going on the x-axis. And that is exactly the same for this polynomial function that we originally started with, this quartic to the fourth degree. However, both to the left and the right, what's happening to those outputs? They're getting larger and larger and larger. They're going up this time. So maybe for the end behavior here, I would write as x goes to infinity, f of x also goes to infinity. And as x goes to negative infinity, or gets smaller and smaller and smaller, well, f of x is still getting big. It's still going to infinity. Now, I write these in the reverse order that your textbook and a lot of things that you'll see online do. I have always thought to myself that we graph points in the coordinate plane by going along the x-axis first and then along the y-axis. So I like to write them in the order of inputs first, then outputs. So when you check your answers in your textbook or online, you'll see a lot of the answers have switched. They'll put f of x first and then x last. I personally like it this way because it corresponds with everything that we've done in the past with relationship to inputs and outputs. Now, I'm not going to answer what kind of degree this is. I'll let you do that after you do the Desmos exploration. Now, what happens when the end behavior is opposite directions? So as you can see in this polynomial function here that we have graphed, on the left, as x is getting really, really small, my outputs are getting big. But on the right, as x is going more and more positive, my y values are getting smaller and smaller and smaller. So what you'll notice is that our outputs are going to be different and our inputs are going to be different. So as x goes to infinity, we'll still be, right? I'm still looking like as x gets bigger here, what's happening to my outputs? Well, it looks like they are going down. They are getting smaller. So we'll say f of x is going to negative infinity. However, as I go to the left and my x values get smaller and smaller and smaller, so as x goes to negative infinity, well, what's happening to f of x? This time, f of x is getting larger and larger and larger. My outputs are getting bigger. Now, if you can't remember exactly what the language is, I would write myself a note in the left margin here. As x goes to something, f of x goes to something. Let's talk about concavity. So our next concept is concavity. And I want you to think of like a bowl of soup. So you either have your bowl of soup facing up and there's no soup dripping out of it, or you have your bowl of soup facing down and all of your soup is falling out. Let's see, this part here looks like my soup bowl is facing down, right? And my soup would be falling out. However, as I continue on, it looks like my soup bowl now is facing up and my soup would be staying in my bowl. Okay, so we call this concave up and concave down. Concave up is where your bowl is facing up. So that's this. I'll highlight it the same color. And then concave down is where your bowl's upside down and your soup's falling out. Now, where the two concavities meet, or where the direction of the concavity changes, that is a very important point, and we call that point the point of inflection. So this point here is what we call point of inflection, or POI. As we get more and more into this, I'm going to want to abbreviate things, so we'll call that a POI. And the point of inflection is where concavity changes direction. And based on point of inflections, you'll be able to determine the degree of a polynomial function. So it's going to help you determine the degree of this polynomial function after you do the Desmos exploration. Let's talk about critical points. Now, these are not new to you. You have explored critical points before. You just haven't had so many of them. Now, another word for critical points is extrema. These are your local maximums. Or local minimums. Now, the words maximums and minimums should be very familiar to you. When we dealt with quadratics, our maximum was our vertex, our minimum was our vertex, but we only had one. Now we have multiple potentially. Let's see, I'm going to put 2 arrows here. So in polynomial functions, you can have many maximums or minimums. So we can't just say that there's one vertex. They are local. They are in a region. They're in a restricted domain. We might have a maximum or a minimum. So I think what I'll do is I'll highlight. Let's see. Actually, let's highlight critical points first. And then I will highlight local maxes. So let's find any maximums that we might have here. So I can see a maximum at this point. And can you see one more? I see another one right here. So I have 2 local maximums. And I also happen to have some minimums. So we'll call those the local minimums. And I can see that I have one here and one here. So I've just highlighted. If you're not using any color, then you might want to draw arrows and make sure that you identify which ones are your local maximums and which ones are your local mins. And as we go forward, I'm going to do the same type of thing with the critical points. I'm going to call these CPs. That way I don't have to write out critical point every time. Or I might say it's a max or a min, but I really mean it's a local max, a local min. So notice here I have 4 critical points. That's going to help you identify something about the degree of this polynomial function. So tomorrow in class, now that you have all this vocabulary, we're going to get into Desmos, and we're going to have you guys do an exploration so that then you can come back and you can identify the degree of every single one of these polynomial functions.